Let us try again. The sound is much better now. I will start again from the beginning. The title to this talk will be Time Domain and Field and Cable Coupling Analysis, and we will focus the problems on EMC applications. As an outline to this talk, we will start with a brief introduction. We will then continue and discuss some concepts on cable coupling, where we will be looking at details around the general cross-sections, how we will combine the different cable paths into harnesses, and then also the different coupling considerations that need to be taken into account. The demonstration will then focus on first building some models, also again focusing mainly on the different coupling mechanisms. We will look at some frequency domain results with looking both at cross-coupling and also radiation. And we will then from there continue to the time domain analysis, which is treated as a post-processing step. And we will be looking at near-field responses there versus different pulse shapes. Okay, so everybody knows obviously that cables are available in many modern electromagnetic systems, and they play a very important role there. As the pictures show, we see these in automobiles, aircrafts, TV ships, and the list basically just continues. The cables obviously have a major impact on susceptibility and emissions performance of a complex system. And in today's design cycles, time is money, so it is important to perform extensive measures afterwards, basically, and to correct the system. But software plays an important role to minimize this time to perform measurements. And therefore, it's important that we already in the design process consider the coupling effects of the cables onto antennas or other devices, and that these should be taken into account. As an example to this, crosstalk and EMC are major concerns for the automotive industry, and as you can see in the car, we have there a cable which we just call the aggressor cable and one which we call the victim cable, and in the back window there is an antenna which does not have an active source. In the picture on your bottom right, we see the near and far field far end crosstalk between the different cable bundles, and we see quite large peaks at around 34 megahertz, which we would ascribe to maybe the aggressor cable being radiating, and then around 38 megahertz where the victim cable is maybe highly susceptible. When we look at the near field plot on the left-hand side, we can see that there is quite a high field near the antenna in the back window, even though the antenna has no active source. If the antenna was to be removed from the model, then the crosstalk, which is at 34 megahertz, was about 8 millivolts, would drop down to about 0.02 millivolts, which basically just tells us that individual systems may appear to be safe, but the complete vehicle has to be analyzed in some instances to ensure that problems do not appear. To the other end, radiation and compliance with EMC regulations is also very important, and in that case we normally look at the maximum electromagnetic field at a distance, say, of 10 meters as a function of frequency. In our scenario, we had a 5-volt differential clock signal, 2 megabits per second digital signal, rise and fall time 100 nanoseconds. We can see the spectrum here on the left-hand side. And if we look at the fields at 10 meters, we can see at the right that we have significant spikes below 30 megahertz because most of the signal spectral content is there, and above 30 megahertz there is less spectral contact, but the cable may radiate more effectively. For FCC Class A limits, these field results are unfortunately not good enough, as it is requirement that, say, at 34 megahertz, the field should be less than the red line, which is at 39.1 dB microvolts per meter. And as an attempt to rectify this and to comply with regulations, in the problem the cables needed to be shielded. We considered some carriers and 32 carriers of 7 filaments each around a cable, and then the field levels drop significantly, as can be shown on the bottom right. Just as an alternative example, where we can clearly see that computer simulations will assist engineers in exploring different scenarios, is an aircraft. Lightning and high-intensity radiated fields are major concerns to aircraft designers, as cables are vulnerable to receiving fields from these. The design phase could potentially iterate through several cycles if the electrical systems require modifications due to susceptibility, and typically one would only in the final verification step actually do measurements for compliance. In this example, the user was interested in lightning, the effect of lightning, and as you can see, the lightning current profile is shown there. Typically, lightning has a very slow decay in the current, which means that if one would have used a native time domain solver, you would have required quite a long time duration and also very narrow time steps. Instead of that, in FECO, we have a low frequency stabilized solution. Because of the narrow time steps and long time duration, it means that one need to look at a frequency domain solution from a very low frequency, and one can then use the frequency domain solution and then apply as a post-processing step different time signals and see what the response would be. And we will be looking at those a bit later again. If we now continue on to the concepts of cable modeling, the first important one is obviously that one would like to support general cross-sections in your model. In typical cross-sections, you might have quite a number of conductors running very close together with maybe insulations around these, and in full wave solutions this is impractical to try and include in the full model because of the geometric dimensions of these. So the idea is that transmission line theory basically bridges the gap between full wave solutions and basic circuit theory, where the approach is basically an extension to circuit theory and a specialization of Maxwell's equations. Multi-conductor transmission line models are basically then a distributed parameter network for each cable cross-section, which is uniform along a specified path. The RLCG is simply, as you would know, is resistance, inductance, capacitance, and conductance in this distributed parameter. And all the cross-section information, both geometrical and material properties, are included in these parameters. And the idea is that from the model we can calculate voltages and currents as a solution to the transmission line equations, and they may vary in magnitude and phase over its length. Just as what we do specifically to FECO is that we assume a transverse EM field. The per unit length parameters are then determined as a static solution to Laplace's equation and to the cross-sectional plane. And we implemented that as a static finite element method solver. In practical examples, we typically do not just have single cable paths. We deal with cable harnesses, which is they are simply an interconnection of cable path sections. Each path will basically have a uniform cross-section, and these are then interconnected by distributed or lumped element circuit descriptions. Each harness will basically be treated as a unit where all the paths will be sharing the same solution setting, which involves the different coupling methods, which will then be radiation, irradiation, or what we will discuss just now is bi-directional coupling. And as I said, we will solve each harness separately using a SPICE circuit description, which will include the per unit length distributed parameter description along each path. The coupling in these will obviously be what we call LC coupling, and there's no direct coupling between the different paths in a harness. The interconnection or termination networks that connect these paths together, they will also be described as lumped elements circuits, and we enforce constraints on the line voltages and currents using Kirchhoff's laws. If we continue to bidirectional coupling, we are typically interested in two types of calculations when it comes to cables. The first is obviously radiation, where the cables would radiate through imperfect shields and cause coupling or problems into other cables and devices and antennas, where we typically would talk about our EMI or EM radiation from a device interfering with the normal operation of other devices. And on the opposite side, we are interested in when cables receive external electromagnetic fields and then again cause disturbances in the voltages and currents of the devices. In other words, our EMC problem, which is our ability of the device to function without errors in its intended environment. Now, in reality, the fields and couple between the cables and the environment in a bidirectional way, because cables would both receive and re-radiate again. And in FECA, we use a method of superposition where we will compute the complete coupling interaction assumed between electromagnetic fields and cables, and also we will calculate coupling between different cable harnesses. In many instances, it may be appropriate or sufficient to only calculate the one-way coupling, and this is a typical simplification which is used in combination with field solvers and MTL. But in certain circumstances, it might actually produce inaccurate results. And for that reason, we will just look at a very simple example here to illustrate this fact. If you look at the picture on the right top, we have an L-shaped cable there, a simple single wire cable with a copper conductivity, a coating around that with a relative permittivity of 3.1. We have some loadings and excitations at the start and end point of this cable, and we have a plane wave incident on the whole setup. The frequency range was 30 to 300 megahertz. Now, if you look at the results at the bottom right, you will see that if we considered the cable to be radiating only, it actually meant that we didn't consider the coupling from the environment, which in this case would be the ground plane and the plane wave to the cable, but only the radiation as a result of the cable being excited by its source. And you would see the green line as the result there. If we do consider the plane wave incident on the cable, you will see that the result matches much more closely to that of the actual full wave solution, which in this case was done by the method of moments. Okay, we will now continue with the demonstration. The focus of this demonstration will again also be on the different coupling mechanisms to actually highlight the differences involved there. I will just start with an overview to the demonstration. It's a basic car model with a predefined cable harness, which you can see in green along the one side of the car. We will be investigating three setup scenarios. In the first instance, we will add another cable instance to run in the same path, where we will illustrate the effect of LC coupling. In the second setup, we will add another cable path and reroute the cable instance or our power cable, which we will define, thereby reducing the coupling and taking routing it further away from the first cable. And in the final section, we would like to introduce shielding to also show the effect on the reduction on cable coupling. We will be looking then at the frequency domain analysis results for intercable coupling and also the radiated near field, and also then the time domain analysis results will be considered on the near field. Just some more information on the basis setup. The generic car model has the first predefined cable harness basically has a two-wire cable running from the front to the back one connectors. These are basically just copper cores coated with SPE coated. They have a core spacing of 2.5 millimeters, and there is a PVC sheath around these wires, which is the green circle surrounding the wires. The front connector, we have a loading between the two wire pins and some parasitic capacitance to ground, which in this case would be the car chassis. And then at the back connector, we have also a load between the two wires. Okay, so our first setup, I will switch now to our CAD-FECA GUI interface, and we will actually demonstrate how we will do the setup. The idea is that we will add an additional cable along this path, which will be grouped in the same cross section as the two wires. And yes, I will return to this slide once we completed that demonstration. Okay, so we have our basic car as a basis here, and we will we have some initialized variables and harnesses defined on the left-hand side. You already see here that we've got the back one and the front. You can see the red dot showing where the connectors are, and we would like to add an additional connector at this point. We open our dialog. We basically have a drop-down list where we can choose our cable start or end point. So I will put it first in the beginning. We are trying to create a power cable, so we just call it PW for power wire, and we will call this connector middle as it is in the middle of the cable path. I would like to add another one, which is at the end of cable path 2. We call the pin to this connector again power wire, and we call this back 2, as we already have a different connector at this point. Now the next stage is that we would like to add a cable instance to that. If we open this dialog, we see here right at the top we have some predefined cross sections. This is the one that is already routed between the front and the back, and then we're interested in adding a single wire now, and we would like to have it between the middle and the back to the newly defined connectors. There's only one path for it to go through, so nothing to be done here. Most importantly, we need to actually connect our signal to the connector pins which we just defined and create the cable instance. If we now go to the cable schematic, we can see here that the middle connector has appeared. The black dot shows that it's been connected, and same here on the left-hand side, the back 2 connector shows with the wire pin PW, and we can now easily add some termination parameters. In our case, we would like to add a resistor, change its properties maybe to a 100 ohms. If you are interested in calculating the current through this resistance, you can activate the probe current button, and we can maybe call it R wire. And this resistance we would like to add to ground. On the middle connector side, we would like to add an excitation. So again, we would add a resistance there, call it R source, and then add a voltage to complete the circuit with to ground. In this instance, ground would be referenced to the card body basically. So this is our first model. Just to return to the slide then, what we have seen in this model now in the setup, we will be looking at the results just after finishing up all 3 setups. It would make it a bit easier to work through the models first. So the idea was basically that we added an additional power cable close to the already existing 2-wire cables. Because it is so close to that, we included it in the same cable harness, in the same cable cross section, which means that we will have LC coupling between those different wires in that cable path. If we, sorry, let's just go back there. If we continue to the second setup, in this case we would like to now reduce the coupling between the power cable and the 2-wire cable. So we are trying to remove it a distance away from the first cable path. Because it is now removed so far, it does not make sense to use the LC coupling anymore, so we would rather define the single wire as a separate harness, in which case we can then consider field coupling between the different harnesses. So the idea of the setup, which I will illustrate, is how we can create a new path that is easy to define a mesh refinement around it, and that we can then route the new wire through this different harness. So if we just return to our CAD Echo setups, if we start with a separate model now, again it looks like the first one that we started off with. And the first step here would now be to create an additional cable path. This might take a moment. So if we go to tools, we would like to enable our snapping to geometry, surfaces and wires, which will allow us to more easily define a path with respect to the existing geometry. So you can see the little point running at the same distance from the geometry. Let's just run it more or less around. And now I'm just going to disable the snap settings again, or set it to 0 so that one can snap to this middle end point there. If we create this, you can see here you've added a new cable path. This was done very roughly now, but you can easily add more sample points to just make it a bit more smooth, but that illustrates the principle. If one would mesh this, then typically there would be no mesh refinement in the vicinity of the cable path. So another feature of CAD Echo would be to easily define a polyline refinement, which if I add this, I can now add points, again snap them to the points around what I previously defined. Let us just define a radius for this, and also the desired mesh size, then we can more easily see where we are moving. Create that. So I'm just going to quickly run the mesh as well so that maybe we can just see what it looks like. Yes, there's another point while we're waiting for this. It is also possible as part of the polyline refinement to actually just import a file with already defined points. So you do not necessarily have to click on the separate points and define it by hand as I just did now. Yes, I can maybe just re-click on this one and then show you that you can have this option to import the points by file name as either an ASCII text file or a NASTRAN file. And if we enable the mesh, you should see that it is now, if we zoom out there, you can see that compared to this area down at the front of the car, you can see a lot finer mesh surrounding the cable path, which will help with the analysis again. Because if we return now to the setup of the actual cable harnesses, we said that we would like to create a separate harness, so we will define a new cable harness. We need to again create some connectors for this harness, and I now know that I just call it cable path end and start. Didn't rename the cable path specifically now. We again call it power wire, and that is the one in the middle. And also we would like to create a second cable connector at the start of the cable path, power wire, and that would be then back to. Easy then to add a cable instance between middle and back to. These are the only connectors now in this harness. because the other connectors which were defined beforehand are all in the first harness defined. You will notice that you have all your predefined cable types available there, so they are not limited to the harness and can be reused. So we select the wire, and then you will notice now that we have two options through which this cable can be routed. And I will disable this and specifically then select that I want it to pass through the new cable path. Again, important that we connect our signal to the power wire pins, create this, and then we can look at the schematic for the second one. You will notice now that we do not have the two wires in the schematic available, because it's available in the schematic for the first one where we've already set up the termination elements. For this one, it's again easy to, I just move this to add the termination elements. I will just show you adding them. I will not be changing the values again, but as shown in the previous setup, it is not difficult to change those. Adding a voltage source and a resistor. Okay, so that is basically our second setup. Most importantly for this one is basically that the idea is that our power cable was now removed at a further distance away from our two wires. Because of the distance, we would still like to include coupling, but it does not make sense to include it as a single cross-section, and therefore we are now considering it in a separate harness with EM field coupling. Our final setup is a bit quicker to do. We will again start with a copy of the first one. Basically the setup looks similar to the first one, but we are now interested in introducing shielding around the two wires to further reduce the coupling between the power wire and the two wire cable. So if we just go to this model, we need to look at where we define the cable cross sections. We have already defined a braid to make things easier. It's a braided shield, which we will solve with the clay formulas. You specify the number of carriers, all the parameters are defined in the picture above. You will see that we apply a coating to the outside of this, and the number of filaments and all the required parameters that is needed. If we look at the two wires with the sheath around it, quite simple to just add a shield. You choose the option that it has a shield, and you select the inside material. And because the shield has already been predefined, no need to change anything here. It will choose as the default the single shield that has been defined. If we apply this, we can now see that if you look at the schematic view, you zoom in a bit, you can see that there are now a different cross-section supported on the first cable path between the back connectors and the middle connectors. Important is that the cable instance has 3 signals now, because the shield is also conductive. We need to also connect that to the connector to have the current flow to the terminal elements. We will have a slightly different termination now. So we will add we will short the shield to the card body, and on the front side we will we will add a capacitance, a parasitic capacitance between the shield and the pin, and then we will also just to make the problem more realistic, add some parasitic elements between the shield and the car body. and in this case we are interested in a very small number. This is just not the perfect short to ground, and all the parasitic elements. So this would complete our third setup. To return to our slide demonstration, just to recap in this scenario, we are again using LC coupling because the power wire is included as part of the cross section with the two wires which are not shielded. But we expect that the shielding will reduce the coupling between the, if we look at the cross coupling between the power wire and the two wires inside of the shield. Okay, so now that we've completed all the setups, we will look at some results. First, in the frequency domain, I have on the left-hand side the currents showing the coupling into the two-wire termination. The load was at the back of the car, the 100 ohm load, and you will notice that the coupling reduced for the models as we expected because of the power wire being closest to the two wires, then being moved away from the two wires, and then adding some shielding to even reduce it a bit further. To the other end, if you look at the radiation, the shielding doesn't necessarily have such a big effect there, so the power wire then still radiates to a point which we set at 3 meters away from the car to have a look. So there are differences obviously in the results, but they are closer, not as far apart as expected for the cross-coupling results. Next we are now moving on to the time domain as a post-processing step in FECO. Basically, if you have a time domain solver, then one would work on the left-hand side. If we have like FECO using the frequency domain solver to obtain the results as we've just seen, this is the result for the setup 1 that we've decided to use. Then if we use a time signal, we know what its frequency response, frequency spectrum is. We can multiply these two in the frequency domain and get a frequency response, and then use the inverse Fourier transform to get back to the time response which we are interested in. The nice thing about this is that we can easily change the time signal, make it wider, make it a step, anything. The frequency spectrum is easily available. The step that took the most time has been run once, and as long as you don't need to change your frequency range, it is a quick step to basically get the time response for different time signals. The nice thing in FECO is also that we have an adapt FECO option where the frequency results are available continuously, so as long as your minimum and maximum frequency didn't have to change, you could use that option and regardless of the time step that is used in post-FECO. Just some basic frequency and time domain concepts that we need to consider in the setup is obviously your choice of frequency range and your choice of time domain or time signal duration. Frequency and time is very interchangeable, so if you have a discrete frequency spectrum, you would get a periodic time signal, and if you get a discrete time signal, you would get a periodic frequency spectrum. For your time signal duration, it's important that your quantity of interest has decayed to 0. Your frequency sampling would then be 1 over your signal duration, which means your minimum frequency is basically just DC plus delta F, which we would then call F min. And important also for the time signal is you need to consider a range based on the time duration and the speed in which your of the medium in which the traveling occurs. In other words, we selected the near fields to be calculated at 3 meters away from the car because 3 meters is well less than the speed of light in this case times the duration set for the signals, as you will see just now. Then we need to continue to calculate the time sampling. Basically, you need to choose a maximum frequency and then set a time step from that. The maximum, or the other way around, choose a time step and get a maximum frequency. The number of time samples is simply the duration divided by the time step, and the number of frequency samples excluding 0 would be the number of time steps divided by 2. If we have this information available and we look at a signal as we allow it in post-FECO, then we can easily choose these parameters. In the slide we show a Gaussian pulse where you can, from the picture, easily know what the different parameters are, the amplitude, the pulse delay, and then also the pulse width in this case. It will show you the signal preview. You can also look at the spectrum preview of magnitude and phase. In this case we chose 2000 nanoseconds, which clearly indicate the signal. The pulse was delayed by 80 nanoseconds and we chose for this purpose a pulse width of 40 nanoseconds. Based on this information, we had the minimum frequency set to 500 kilohertz and we sampled up to 100 megahertz, and that is the reason also why our frequency results were chosen to be that specific frequency range. The time step is now 5 nanoseconds, and that meant from the equations that we had to have 400 time steps. I will show just now in post-FECO as well how the setup looks. If you just continue to the next slide, is that, maybe I should first show in post-FECO. We have here the near field results for, maybe I should do this. We have the near field results for our first setup. If we create a new graph, okay, so we have already pre-set up some time signals, which we call Gaussian 40. If we open this dialog, this is the same as the last slide that I've shown you. Just to illustrate, if we make this 100, you can see that the pulse width increases. You have the spectrum on this side. If we change it to be a narrower time signal, you will see that the spectrum will be a wider spectrum. So it is quite easy to change the parameters and see what the spectrum or the signal will preview like. We have a couple of default options here that you can choose from. You can specify your points manually, or also enter an equation in terms of time. With time you're changing variable. So from this, basically, if we now look at the near field results in time, we can see here, okay, let's look first at this. With the spectrum, if I add the time signal spectrum on this graph, I will just, to make it a bit more visible, multiply this signal and change it to frequency. You will basically see the spectrum overlapping here, or having spectral content in the lower frequency range. And basically from this we will have still the resonance here at 25 megahertz filtered into the spectrum. So what we will see when we look at the time domain is that we have a pulse duration, a pulse period of 1/25 megahertz, which is 0.04, which matches that single frequency that was filtered out in the results. Maybe just a bit more clear to show on these slides is if we look at the frequency response on the left-hand side, we can see the 25 megahertz resonance there. If we then multiply the frequency response of the time signal with this field, we will get the response on the right-hand side top, and you can clearly see this resonance still visible in there. And then if we take the inverse Fourier transform of that, you will see the time signal that I've just shown you, which is the near field time response for the Gaussian pulse of 40 nanoseconds width, and this matches then the signal period of 0.04 microseconds. If you're not happy with the 40 microsecond Gaussian pulse, you may want to change it and rather make it a 20 microsecond pulse. Because you now have shortened the period, it becomes a wider bandwidth in the frequency domain. Again, if you look at the filtered result, rather than only the 25 megahertz resonance present, we also see now higher frequency content passing through. And if you now take the inverse Fourier transform of that, you will ultimately get the green result with a much finer time period because of the sort of interference between the different resonances. You do not have an exact period here that you can match to any of these resonances like in the first scenario, which was specifically chosen to illustrate this, but it makes sense that it should be narrower or shorter because of the higher content that is, frequency content that is visible in there now. Okay, so as a next step, we look at the totally different signal. I've chosen the double exponential pulse here. Again, we have some rise time, some delay, and you can see the frequency spectrum on the right-hand side with the phase. We did the same sort of calculations, chose a signal duration to make sure that the step has died out, added the pulse delay, chose our minimum or set our minimum frequency based on the signal duration, chose the maximum frequency and calculated the time step and the number of time steps. I've plotted the results here just with overlay with the step to illustrate how the signal switches basically as the step switches. We can also see that from this we said that we want a 50 nanosecond pulse delay, and we can also see here that only once we reached 50 nanoseconds as the pulse actually started coming through. Just a simple change, you might not be happy with the double exponential pulse in its form that it was. So you can also then adjust it to your own needs. In this case, it was adjusted very slightly to produce a bit more of a filtered response, which you can see in the bottom left graph. And then on the right-hand side, again, we just show the time field results of the pulse filter, now a bit dampened more as compared to the original results, which is expected based on the frequency spectrum. Yes, so this would conclude our presentation. We basically focused on the concepts of cable coupling and highlighting the differences between LC coupling and field coupling. And in the demonstration, we showed some frequency domain results highlighting these concepts of the cable coupling, and then how one would, as a post-processing step in post-FECO, add time signals and look at the time domain results.
Thank you, Marlies. It would be quite difficult to answer all the questions now, so we suggest that you either contact your local reseller, or you can contact somebody from EMSS SA or webinar@emss.co.za, and we will then handle some more questions. We will also make the presentation available as a recording, and that link will be sent through to you as well. Thank you very much.